back. I'm delighted to welcome Professor Emily Riehl to give the 2025 Hardy Lecture titled Could Infinity Category Theory be Taught to Undergraduates or to a Computer? Emily is the Kelly Miller Professor of Mathematics at Johns Hopkins University, working on higher category theory, homotopy type theory, and computer formalization. Emily studied mathematics at Harvard University, where she graduated in 2006. She gained her certificate of advanced study in mathematics with distinction from Churchill College in 2007 and earned her PhD from the University of Chicago in 2011, where she wrote her thesis on algebraic model structures advised by J. Peter May. Emily runs the Johns Hopkins Categories Theory Seminar, is the co-organizer of the Homotopy Type Theory Electronic Seminar Talks, and was a founding board member of Spectra, the Association of LGBTQ+ mathematicians and their allies. She is the author of numerous books, including Elements of Infinity Category Theory with Dominic Verity, published in 2022 by Cambridge University Press. She serves on the editorial boards of numerous journals, including Homology and Homotopy. Sorry, it's one journal. I thought, wow, there are a lot of journals. Homotopy and Applications, the Bulletin of the AMS, and Zeitschrift für mathematische Logik und Grundlagen der Mathematik. In August 2024, she was announced as the LMS Hardy Lecturer for 2025. The Hardy Lectureship was founded in 1967 in memory of G.H. Hardy, in recognition of outstanding contributions to both mathematics and to the society. Hardy was one of our presidents, and he also was one of our major donors. The Hardy Lectureship is a lecture tour of the UK by mathematicians with a high reputation in research. And this is the penultimate date in Emily's lectureship tour, which has taken her to Aberdeen, Manchester, Glasgow, Edinburgh, Cardiff, Cambridge, and Birmingham, and a final date in Bristol on Monday. Beautiful city, you will like it. That's where I'm from. When she was awarded the lectureship, Jason Lotai, here on my right, chair of the Society Lectures and Meetings Committee, gave her the following citation. Professor Riehl has established herself as a leading expert in higher category theory and has also developed an interest in connections with computer science, such as homotopy type theory. She is an accomplished and enthusiastic expositor of mathematics at a variety of levels, aimed at mathematicians, as well as popular writing with articles in Scientific American and New Scientist. She also plays a leading role in broader engagement of mathematicians and other scientists from marginalized and discriminated against groups. Please give a warm welcome to Professor Emily.
Great, thank you very much. I want to give thanks also to the London Math Society more broadly, to Kieran O'Connor in particular for everything you've done to really set this up, to Andy Baker and Tom Lenster, who are the ones who put me up to this, to Clark for that wonderful talk. It is a particular honor to be delivering a lecture series named Dr. Hardy, who is one of my sort of first mathematical heroes. I read A Mathematician's Apology when I was a high school student and an aspiring mathematician, and was struck by these poetic descriptions of the timeless beauty of a mathematical proof, and also by a detail in the bibliography of him written by C.P. Snow in the edition that I read, which described his workday involving sort of 4 hours of research in the morning, followed by an afternoon spent watching the cricket. I found that particularly aspirational, not the cricket specifically, but the fact that you could make a real contribution to mathematics without having it be the only thing you do during your life. So, okay, so I should start by explaining the title. So, could we teach infinity category theory to undergraduates? Maybe is asking a question about in sort of a hypothetical future, would it be possible to teach this very complex mathematical topic that Clark introduced to students, maybe as part of their undergraduate degree or they're doing a master's course, sort of as one of the routine prerequisites in a mathematical education before specializing at a research level. To a computer, I mean, in the sense of computer formalization. And I had assumed that it would not be obvious that we would even want to teach infinity category either to undergraduates or to a computer, though there was a supportive question asked in the last talk. So I'm actually going to start with some motivation about why infinity category theory and even why category theory. Why should we teach category theory to students? So in other words, what is category theory for? So when I was starting to learn some more formal mathematics, one of the facts I learned about functions, if I have a function from A to B, then I get some functions between the posets of subsets, the power set, P of A and P of B. There's the inverse image function and there's the direct image function. And a thing that really bothered me was that the inverse image function is so much better behaved in the fact that it respects both unions and intersections, whereas for the direct image function, that was only preserves unions. Direct image of a union is a union, but not necessarily the case for intersections. That really bothered me. I had no idea why this would be so different. Later on, taking linear algebra, I learned that for vector spaces U, V, and W, the tensor product of U with the direct sum of vector spaces V and W is isomorphic as a vector space, so linearly isomorphic to the direct sum of the tensor products of U and V and U and W. In an abstract algebra course, I learned that if I have groups G, H, and K, I can take the Cartesian product of the group G with the free product of the groups H and K. And that's isomorphic in the sense of group theory, so group isomorphism to the free product of the direct products of the Cartesian product of G and H and G and K. And what I understand now is that all of these results are true for the same reason and have the same proof. So these are all instances of a general theorem that you can state in the language of category theory. The theorem is that something called left adjoints preserve coproducts. More generally, left adjoints preserve colimits, but I'm going to focus on the coproducts, which will be a little bit simpler to define. So these theorems are all special cases of this abstract result. A fun fact about category theory is when you prove a theorem in category theory that involves a sort of generic category variable, then it has a dual theorem, or really it has 2 to the n duals for however many categories n appear in the statement. In the case of this one, there's a left adjoint functors between 2 different categories, so there are actually 4 dual versions of the theorem. Left adjoint functors preserve coproducts. The sort of most common one is that right adjoint functors preserve products. And this, by the way, completely resolved the confusion that I had when I was an undergraduate. So this direct image function, order preserving function between posets induced by a function between sets is a left adjoint. So it preserves unions, which are coproducts in the poset. Whereas the inverse image function, the one that goes in the other direction, is the right adjoint of that. So it preserves intersections, but it is also a left adjoint. There's another sort of push forward construction between posets that I only learned about much later. And because of this inverse image is both a left adjoint and a right adjoint, it preserves both the coproducts and products. Okay, so I've stated a theorem using a bunch of terminology that I have not defined, and I won't define it just yet, because I want to make the point that the sort of general argument suggested by category theory gives a pretty nice proof of these results in any one of these examples. And so let's do that in the setting of linear algebra. So I'm going to prove for you now that for vector spaces U, V, and W, the vector space defined by the tensor product of U with the direct sum of V and W is linearly isomorphic to the vector space defined as the direct sum of the tensor products of U and V and W. So we'll construct an explicit linear isomorphism between these vector spaces. So the strategy is going to use something called the innate lemma, which is another result in category theory. This is the fundamental theorem of category theory, if you will. And what it says is that if you're trying to define an isomorphism between 2 objects in any category, so in this case, vector spaces in the category of vector spaces and linear maps, what it suffices to do is give a natural correspondence or a family of bijections between maps out of those objects and into a generic object X. So in other words, here, the task is to show that if I have any there's a natural correspondence between linear maps out of the tensor product of U with the direct sum of V and W into X, and linear maps out of the direct sum of the tensor product of U and V and U and W into X. So if I can show that there's a correspondence between these things, by which I just mean a bijection, and moreover, this has to be natural, which is a technical term in category theory that I'm not going to define, then it follows that these vector spaces are isomorphic. And it seems like I've made a simple, replaced a simple statement with a more complicated statement, but it does actually help in the proof, which we'll see. So what I get to do is I get to start now with a linear map out of the tensor product and into an arbitrary vector space X. And a defining feature of the tensor product of vector spaces is that linear maps out of a tensor product correspond to bilinear maps, so functions of two variables out of the two constituent vector spaces separately. And by Currian, I can think of a bilinear map as a linear map, in this case, out of the vector space V direct sum W into the vector space of linear maps from U to X. So essentially, by definition of the tensor product, really by adjunction, which is the abstract categorical step that I've just invoked, a linear map from the tensor product U tensor V direct sum W to X corresponds to a linear map out of the direct sum of V and W into the vector space of linear maps from U to X. So that's the first step. And now equally a defining characteristic of the direct sum of two vector spaces is that if I want to define a linear map out of a direct sum of vector spaces, it suffices in the subspace W. So there's a unique way to extend an arbitrary linear map defined on V and on W to a linear map out of the direct sum of those vector spaces. So in other words, linear maps from V direct sum W into the vector space of linear maps from U to X correspond to pairs of linear maps, one from V to linear maps from U to X and one from W to linear maps from U to X. But now at this step, I can use the defining property of the tensor product again. A linear map from V to linear maps from U to X is just a bilinear map that corresponds to a linear map out of the tensor product. This is the defining property of the tensor product. So in other words, I have now two linear maps, one from U tensor V into X and one from U tensor W into X. And then again, by the defining property of the direct sum of vector spaces, those pair uniquely to define a linear map out of the direct sum of the tensor product of U and V and U and W into X. So that, by the innate lemma, completes the proof. And what might not be obvious is that also constructs an explicit linear isomorphism between vector spaces. So what I'm after all, is a linear map from U tensor V direct sum W to U tensor V direct sum U tensor W. And I can extract those linear maps by specializing the arbitrary vector space X to be one of these two vector spaces, starting with the identity linear map and then passing it through the explicit bijection that I just described. So if I start with an identity at top and pass it through at the bottom, I get a linear map in this direction. And if I start with the identity on bottom and I pass it back through the bijections going up, I get a linear map in the other direction. And these are inverses. So these two linear maps are inverse isomorphisms by this naturality condition that I have not mentioned. So that is the proof of the distributivity of the tensor product over the direct sum in the setting of linear algebra, but it equally well proves all of the other theorems in the other case, which would be more clear if I had introduced the abstract language, which I'm not doing just yet. Okay, so this is meant to give some indication of sort of what category theory is all about, sort of what it can do for the rest of mathematics. So this single abstract result, left adjoints, preserves coproducts, have a lot, has various consequences in various settings. So the fact that the direct adjoint image preserves union, tensor product distributes over direct sums, Cartesian product distributes over free products. And I would argue that these abstractions from category theory, I mean, certainly it takes some getting used to, but I think they're helpful in various ways. So one thing they can do is they can clarify arguments. So, that proof I stated in the language of linear algebra. I didn't need to introduce these categorical concepts to give that proof. But you might wonder, is it important somewhere in this argument that we're dealing with free modules, that we're talking about vector spaces and not modules for a ring? That's a natural question to ask, and the sort of abstraction makes it clear that the setting is no. It also gives a relatively elegant proof. There are other arguments that would use a basis, or say in the finite dimensional case, these have the same dimension. It's sort of guiding you towards a more general proof. It can shorten the proof. I mean, if you want to avoid using a basis but just explicitly describe these functions, then you have to check that they satisfy all of these relations that characterize the tensor product, and we completely avoided that messy definition. So another useful thing is they can help generalize constructions and proofs to other settings. So in the context of group theory, it's maybe not obvious whether the Cartesian product should distribute over the free product or the free product should distribute over the Cartesian product. So the fact that one of these constructions is the left adjoint and the other is the coproduct is what makes it clear which statement should be correct. An extension of this to the setting of topology would be more subtle. It is true that the Cartesian product of topological spaces distributes over coproducts, but if I had generalized to general colimits, now there's a subtle point set topology hypothesis that one would have to put on the topological space. And again, the reason that is so is because we want the Cartesian product to be a left adjoint. So the abstraction is guiding you to the correct statement in that setting. And another thing is this just helps you upload more complicated mathematical ideas into one's working memory. So I'm a mathematician with a terrible memory. And what I use my category theory for is isolating the formal stuff when I'm learning a new subject from the things that I actually have to focus on. So there's things that are true for very general reasons that you don't have to worry about. So you have brain space to deal with something more interesting. So in summary, so category theory defines a language that supports a lot of 20th century mathematics. This caveat is of course very important because I recognize there are probably lots of folks in this room who work in areas where category theory hasn't really touched, but there are other areas where it really is sort of essential. It's essential in particular often to just define the objects that mathematicians study. So, I think in many fields, some advances have been made with the introduction of a new definition, a scheme, for instance, and it's hard to imagine those definitions being so easy to state and work with without categorical language. Okay, so that's what's category theory for. What is infinity category theory for? So I realize I haven't given any definitions yet, but Barry Mazur has a sort of lovely sort of metaphor for a category. He describes it as a category still in the ordinary sense. It frames a possible template for any mathematical theory. The theory should have nouns and verbs and objects and morphisms, and there should be an explicit notion of composition related to the morphisms. So I think of this sometimes as an insight that Emmy Noether and members of her school contributed to group theory. If we're interested in groups as mathematical objects, there are properties of groups that are more easily expressed once we introduce group homomorphisms. So the morphisms between groups into the story. You can characterize a construction about groups, for instance, the free product that I just mentioned, by means of a universal property before you give an explicit construction. So there's an extra richness to the theory, maybe an extra motion, an extra verb to the theory provided by the morphisms. And so that's what a category is. It has some mathematical objects, it has some transformations between them. Those transformations can be composed. So extending the metaphor, sometimes you need a richer vocabulary to describe mathematical objects. So maybe you need adjectives, adverbs, pronouns, prepositions, conjunctions, interjections. Maybe these morphisms have some sort of morphisms between them, or there's some sort of richer language that's needed. And that's vaguely what an infinity category is. So the data it has are some objects, which we can picture as being points, maybe in a space like this sort of exit path space, and morphisms between them, which we've always drawn as arrows, and now I'm going to label as one morphisms because we think of that as the one-dimensional components of the category, the points and the morphisms. And then there's sort of a new idea. So, this category theory is all about compositionality. So we need to have some sort of composition for morphisms. But what's forced by examples is to relax the idea of composition. So in an ordinary category, we think of composition as a sort of partially defined binary operation. If you have a morphism from W to X and a morphism from X to Y, then there's a composite morphism from W to Y that's called G composed F. In an infinity category, what's forced by the examples is to admit that any morphism from W to Y that's sort of connected by an invertible higher dimensional morphism maybe in the way that we're envisioning by this triangle, any morphism like that is a composite of F and G. So more precisely, any pair of composable morphisms, the F and G, have a contractible space of composites. So there's a homotopical uniqueness, but it's not sort of a function in the traditional sense where two morphisms would have a unique composite. And similarly, these witnesses to composition, these invertible two morphisms are data. The motivation for passing from a one-dimensional category to an infinity category is you might need that data as an input to a further construction. And so associativity now becomes more complicated. So usually associativity would say if I have three composable morphisms FGH, that the binary composites in either order results in the same thing. The way you understand that here is you have some two-dimensional witness alpha to a particular composition between F and G, and another two-dimensional witness beta to a particular composition between G and H, and another two-dimensional witness gamma to a particular composition between F and the composite of H and G. And then there's a fourth witness that isn't displayed in this picture, which is in the sort of back triangle, which is to a composition between the composite G and F and H. And those four witnesses form the boundary of a three-dimensional region of tetrahedron in the way I've drawn it here. And associativity is given by the data of an invertible three-dimensional morphism that has as boundary the data that I've just described. And unfortunately, it does not stop there. So if associativity was an equation, then ternary associativity applies quaternary associativity and fivefold associativity and so on. But really, there's higher coherence conditions involving the data that I just described that witnesses this associativity. Plus, we have inverses and unit identities and so on and so forth. So I haven't given a full definition yet, but I've given an impression of the definition. And I want to now try and sketch some examples to complement the examples that Clark gave. So I'm going to start with one category that may be a little bit more familiar. This is the fundamental groupoid of a topological space. If you're familiar with the fundamental group of a topological space and your space is path connected, then this is equivalent to the thing I'm describing here. But in any case, this is an ordinary category whose objects are points in the space. So as Clark noted, there are a lot of points in the space, but it's okay because most of them are isomorphic. And then arrows are paths in the space up to based homotopy. So an arrow has a direction, has a specified source and target. If there's a homotopy that fixes the starting and the end points, then we consider those as defining the same arrow from the point of view of getting an ordinary category. These images are not AI generated. I've credited the artist. So for instance, the example that Clark mentioned, the fundamental groupoid is equivalent to of a circle is equivalent to the fundamental group of a circle, which is Z. So because we don't have homotopies between sort of paths that wind around some integer number of times in some direction. Okay, but the problem with this is this doesn't see the higher dimensional structure in a space. So one of the things that Clark alluded to is that as soon as n is greater than 1, the homotopy type of the n sphere is not truncated. So there's sort of interesting information in arbitrarily high dimensions, but this fundamental groupoid is trivial as soon as n is greater than 1. So it's not distinguishing between these different spheres. It doesn't see the higher dimensional structure space. So instead, something that captures the full homotopy type of a topological space, so the information provided by all of its homotopy groups, is called the fundamental infinity groupoid. So in one sense, this is a way less familiar construction because it involves something called an infinity groupoid, which nobody's heard of, but it's also sort of more natural from the point of view of describing the algebra of paths in a topological space. I should say if you've encountered the singular complex in defining singular homology, that's a avatar of this fundamental infinity groupoid. So what is it? So infinity groupoid means infinity category, but where all the morphisms are invertible, including those at dimension 1. So its objects are points as before, and its one morphisms are paths. And this is already a point of difference. The one morphisms in the fundamental groupoid were based homotopy classes of paths, so equivalence classes of paths. Here, every single path is regarded as a distinct one morphism in the fundamental infinity groupoid. And what these based homotopies, how they appear is they are now two morphisms. So they're named explicit data given by the invertible two morphisms, and we can have higher homotopies between homotopies, which I've sort of attempted to draw in this thing as the 3 morphisms and homotopies between homotopies between homotopies, and the 4 morphisms and so on and so forth. So that's what this is. Okay, so any infinity category has a quotient that is an ordinary 1 category. You form this quotient by sort of taking the same objects as before and then identifying any 1 morphisms that are connected by an invertible 2 morphism at all. You forget all the higher data, use the invertible 2 morphisms to define equivalence classes on the 1 morphisms, and that's this quotienting process. And that exactly turns the fundamental infinity groupoid back into the fundamental 1 groupoid, which is an ordinary category. So any infinity category has a quotient homotopy category. We're covering the thing that's a little bit more familiar, but this is better because this has the full homotopy type, whereas the fundamental groupoid does not necessarily. So Clark mentioned the homotopy hypothesis of Grothendieck, which he described in a more general setting. What it says is that the fundamental groupoid defines an equivalence between spaces up to weak homotopy equivalence. So between homotopy types, which are the information, sort of the weak homotopy equivalence classes of spaces, I guess, and infinity groupoids up to equivalence. So this could be, if infinity groupoid is an undefined concept, this could be a definition of infinity groupoid, and infinity groupoid should just be a homotopy type, making this trivial. If you want to give a particular presentation of infinity groupoids or another definition of infinity groupoids, then this is a desideratum that should be proven as a theorem. So for instance, Daniel Quillen proved it using the complex models of infinity groupoids, established this equivalence. And I wanted to mention as well, there's sort of a new word on the street for infinity groupoids. So anima is a synonym for infinity groupoid or homotopy type. By the homotopy hypothesis, these are all the same. And the way you think about it as sort of spaces, but it's spaces in the homotopy theorist sense. So not at all in the geometer sense, spaces only up to homotopy equivalence. In particular, you can't distinguish between contractible spaces in the sense of infinity groupoids. Right, so what I've recalled here is sort of our first example of an infinity groupoid, the fundamental infinity groupoid of a topological space and its quotient ordinary category, which is the fundamental 1 groupoid of a topological space. And I want to mention 2 other examples, in each case you may have heard of the quotient 1 category, if not the infinity category that has that 1 category as a quotient. So one of them is something called the derived category of a ring. So this is an ordinary category. It depends on who you talk to anymore. Some people want to use derived category to mean the infinity category. So I always have to ask when somebody says derived category. But traditionally, the derived category of a ring was an ordinary 1 category, but it's a 1 category whose morphisms are described by some sort of complicated quotient process, or maybe by freely inverting something. So that's a quotient homotopy category of an infinity category of chain complexes. And so what is this infinity category of chain complexes? So its objects are chain complexes of modules over whatever ring we're talking about. Its morphisms are chain maps, so the sort of ordinary morphisms. But then we're adding in some higher dimensional morphisms. There's something called a chain homotopy, which is a degree 1 map. And then we have degree 2 maps and degree 3 maps and so on. And that's giving the higher morphisms in this infinity category of chain complexes. And then if we do this quotienting process, we recover the derived category. Then there's also a sort of classical homotopy category of spaces, the sort of original homotopy category. We think of this as the category of homotopy types. And that's again a quotient homotopy category of the infinity category of spaces. And what is this category? So its objects are topological spaces, and now I really mean spaces, ordinary spaces. Morphisms are continuous functions between spaces, so that's again kind of an ordinary category that we're starting with. But then we're adding on these higher dimensional morphisms. So we can have homotopies between continuous functions, those are the invertible 2 morphisms, and homotopies between homotopies, which are invertible 3 morphisms, and so on and so forth. So these are 2 less geometric, but kind of as concrete as it gets examples of infinity categories. And I've done the same thing that Clark has done for sort of the same reason. I haven't yet given you a definition of an infinity category, but very roughly, the way we can think about it is it's a weak infinite dimensional analog of an ordinary 1-dimensional category where I have these objects and 1 morphisms and then invertible higher morphisms, so invertible 2 morphisms, invertible 3 morphisms, and so on. But I'm also weakening all of the category structure, and that was a little bit less apparent in these examples, but it's is essential in this sort of fundamental one group word. You might think you know how to give an explicit definition of a composite of 2 paths, but your explicit definition is not associative. So it's better to admit sort of the possibility that I mentioned before, where there are many different paths that represent a composite of 2 paths, and that representation is witnessed by some higher dimensional data. That's a morally correct perspective. Okay. So what is infinity category theory for? Well, one motivation is there are some constructions that are classically understood as taking place in this setting as the derived category of a ring, or maybe the homotopy category of spaces, that are sort of meant to be analogous to colimit constructions, which are ways to take objects of some category and produce new objects in that category, but aren't actually colimits. So these go by the name homotopy colimits. And the example that I've illustrated here is something, I'll just describe the algebraic setting, taking the mapping cone of a chain map. So if I have a chain morphism between 2 chain complexes, I can form a new chain complex. That's the thing I've written C of F with the bullet. I won't review the definition now, but it's a useful gadget. It's acyclic if and only if that chain map is a quasi-isomorphism. But it doesn't have a universal property. So it's a construction that makes sense in the derived category in that it's invariant under the quasi-isomorphism, which is the sort of notion of isomorphism in the derived category. But it doesn't have a universal property. So it sort of resembles a colimit, but it's not a colimit. And in particular, the theorem that I mentioned at the beginning, left adjoints preserve colimits, does not apply because it's not a colimit. So these are ordinary 1 categories. There are several adjoint functors between them, but I can't apply this theorem because these objects don't have a universal property. And the solution is to situate them where they really belong. So the squares that I've described here, so this one in the setting of the derived category and this one in the setting of the classical homotopy category of spaces, lift to the infinity category of chain complexes, or I guess I said cochain complexes, and the infinity category of spaces. And in that case, they commute up to one of these invertible 2 cells. So there's some data that's associated with this construction that you can't name in the derived category because you've quotiented out all the higher homotopy stuff. So this mapping cone comes with a canonical homotopy that inhabits the square that I've drawn there. And if you keep it around, now this object does have a universal property. It is a colimit, not in the classical 1 categorical sense in the derived category, but in the infinity categorical sense. And so the infinity categorical analog of the theorem, left adjoints preserve colimits, applies. And so this is kind of what infinity category theory is for. There's settings where you need this extra information for your construction to have some sort of universal property. Okay, so I want to sort of approach a definition or sort of apologize for not having given a definition. So another perspective on what infinity categories are is they're like ordinary categories, but where all the sets in the definition of an ordinary category are replaced by these infinity groupoids, also known as homotopy types, also known as anima. So there's some analogy between sets and infinity groupoids and categories and infinity categories. So a category has a set of objects if it's a small category, and has Hom set of arrows, so sets of morphisms between any 2 objects. So infinity categories then have an infinity groupoid of objects and infinity groupoidal mapping spaces. That's well enough. But what's complicated is that the rest of the category axioms, they're sort of expressed in the language of sort of set theory and first order logic. In particular, we have this composition function satisfying some axioms like associativity. And in infinity categories, I've been emphasizing composition isn't really a function. And maybe part of the issue is that we think of infinity groupoids as sort of presented by spaces, but they aren't really spaces. They don't have a well-defined set of points. They have a well-defined set of path components. And it's just difficult to sort of express this fully precisely. And this is why everybody who gives a talk about infinity categories tries to avoid defining them. You don't really want to see the definitions. So this is the slide where I give some definitions. I mean, one of the reasons you don't want to see them is different researchers in the area use different definitions for different reasons. I've described both of these as presentations of infinity categories. They're sort of, Buraki would consider this a definition. So that's maybe a way to think about it. So one is something called a quasi-category. Another is something called a complete Siegel space. I'm not going to go into these definitions at all, but I wanted to acknowledge they exist and make the point that this does not explain in an obvious way sort of either of the perspectives on infinity categories that we've taken so far. So, in this bisimplicial set, where are these invertible two morphisms? It's maybe not entirely clear. How do we know that composition is well defined up to a contractible space of choices? So this is sort of why the theory is complicated to teach to anybody, much less sort of undergraduates. And it's not as if it's not rigorous. So there's a lot of work. So the definition of quasi-category is originally due to Boardman and Vogts, further developed by André Riehl and Jacob Lurie. The definition of complete Siegel space is originally due to Charles Rusk. There are lots and lots and lots of papers developing the mathematics with these definitions. So the theory exists, but the problem is it kind of takes too long to learn. So there's a lot of work, increasingly work in other fields, maybe in Langland's, where it's sort of hard enough to understand the mathematics in the other area in those papers, much less the prerequisite infinity category theory. So, some of my colleagues in number theory want to read these papers and don't have time to learn infinity category theory because they're sort of doing other things. So, the only way that I can think of as sort of answering this question of where will researchers in these areas find the time to learn infinity category theory is that maybe in the future they'll have learned it along the way, like they learned everything else. Like I learned a bit of functional analysis and everything. So sort of the pithy way to express that is how will we teach infinity category theory to undergraduates, not today, but in the future. Okay. And here's my best guess. So I've been thinking about this problem for several years, and my best guess as an answer is that this would be a lot easier if the foundations of mathematics, meaning the sort of way that I could give a precise definition of an infinity category, is so far away. So the problem with infinity categories is they're not really built out of sets in the way that most objects defined in set theory are. There is another formal system so what they're built out of is homotopy types, and there's another formal system, another foundation for mathematics in which the homotopy types are the primitive objects. And so if we were starting with homotopy types, and then we just had to build infinity categories, that definition would be a lot easier both to state formally and also to work with. So that's kind of the dream for the future. And now I'll show you the plan for the talk. I'm through the first two sections already. So I've given some indication about what category theory, the role it plays within mathematics, what infinity category theory is for in mathematics. And now I want to explain this dream. So how, if we were working informally in another system, we could actually give definitions, not just of infinity category, but of the left adjoint functor and the coproduct, which I will get back to eventually, and also teach it to a computer. Okay. So what is homotopy type theory? So this is another formal system for mathematics. It's a standalone way to develop mathematics that can be interpreted back in traditional foundations, and traditional foundations can be interpreted in here. It's better not to worry about that interpretation because it's quite complicated, and that's sort of where the magic is, but to think of it as sort of a standalone formal system for mathematical constructions and proofs. It's a way to understand what mathematics is. So the basic objects here are called types, and we can think of them as being spaces or infinity groupoids, really more properly homotopy types rather than topological spaces. And in this formal system, because it's sort of by nature constructive, all constructions are automatically continuous or equivalence invariant. So this is a system that's somehow automatically derived. We can think of it as the sort of synthetic theory of homotopy types, and that the primitive types are just homotopy types. So they're right there rather than something I have to give a complicated construction of. And it's also a homotopical interpretation of a previously existing system of type theory, specifically dependent type theory, in the form devised by Martin Luft as a foundation for constructive mathematics in the 1970s. So a thing was the hardest for me to grasp when I was starting to learn about this is that something that is separate in traditional foundations. So traditional foundations are given by set theory, which is where all the stuff lives, and then first order logic, which is where the proofs live. They're treated together in dependent type theory and homotopy type theory. So in other words, types can play a dual role. They're used both to describe mathematical structures, but also to encode mathematical assertions. So I will state a theorem in homotopy type theory by constructing a type that somehow encodes its statement. So when a type is encoding some structure, a term in that type is maybe a particular instance of the structure. When a type is encoding a mathematical statement, just forming the type doesn't say that the statement is true, it's just saying that the statement is grammatical. This is a well-formed sentence in mathematics, in this sort of mathematics. To prove it, I need to then supply a term of the type. So a term can be thought of as a proof. So sometimes this goes by the slogan, propositions as types. And how you should think about that is propositions are sort of special cases of types. So in general, types might have non-trivial higher dimensional structure. So they might be sets, or they might be one types or two types in the sense of homotopy theory. But propositions are somehow a special case. So the logic is kind of along for the ride with all the constructions. Okay, so homotopy type theory has as primitives these types. So for example, so everything in red going forward will be a type, right? And nothing that's not in red is a type. So types, for instance, there's a type of natural numbers, a type of real numbers, a type of groups. These are all examples of types as encoding some sort of mathematical structure. Another primitive are the notion of terms. A term always belongs to a specified type, so there aren't kind of terms out in the ether. Every term belongs to its particular type. So for instance, there's a 17 that's a natural number. There's a different 17 that's a real number. The square root of 2 is a real number. Klein-Ford group is a term of type groups because it's an instance of a group. And then we also have these type families. So every time I give a talk, I change my mind about what syntax is the best, but the one I used here. So I should think of this as for a variable term x of type A, I have a family of types B of x. Or for a variable term x of type A, and another term y of some type that might depend on that x, a family of types C, X, Y, depending on both the x and y. So for example, depending on a natural number n, I have the mathematical assertion n is prime. It's a grammatical sentence in mathematics. It's not always true, but for every n, I can form a mathematical sentence that asserts that n is prime. So that's an example of a type family where the types are encoding a mathematical proposition, a grammatical mathematical proposition. Another example is for every natural number n, I can contemplate fields of characteristic n. Again, there aren't necessarily examples for all n, but it's a concept you could describe, a field of characteristic n. Given a group and a field, I can consider the type of representations over that field, of that group over that field. And then the final primitive is something called term families. So a term family, it's really, you should think of it as a function from the left-hand side to the right-hand side. So to have a term family, that means for all x and x, I have a specific term b of x of type b of x. And in particular, I'm not going to have any examples of term families in these first two type families because they aren't always inhabited. So because I cannot prove that 4 is prime, there's no term family that sort of inhabits the first type family. And because I cannot construct a field of characteristic 4, there's no term family that inhabits that type family. But if I change my mind and talk about rings of characteristic 4, then that's no problem. So an example of a term family is for every natural number, I can define the ring Z mod n, which does have characteristic n. So I've defined a family of terms there. And similarly, for an arbitrary group and an arbitrary field, I can construct the ring of regular representations, and then that's an example of a term family as well. Okay, so this is the sort of basic stuff in homotopy type theory. And what animates both constructions and logic are these rules for building new types and new terms from given types and given terms. So it's called a formation rule when I'm building a new type out of given ones. So in particular, I can form product types and coproduct types and function types. So this entire expression in here is a name of a single type whose terms you would think of as functions from A to B. I can also form new types out of type families. So something called the dependent subtype and the dependent product type. There's also something called the identity type, which is going to be the way that we reason about mathematical equality in this system. And these again come with rules that tell us about the terms in these types. So it's hard to know how to think of this. Here's a table, which for the purposes of today's talk, we should think about as an analogy, though there are theorems that sort of validate these sort of interpretations. So I can think about a type in a logical sense as encoding a mathematical proposition that may or may not be true. I can think of it as encoding a set. In the homotopical interpretation, I can think of it as a space, or really better as a homotopy type. A term of that type we then think of as a proof of the proposition or an element of the set or a point in the topological space. Then I have an empty type and a singleton type for the true and false propositions, or the empty and singleton sets of spaces. These operations of forming the product type, the coproduct type, the function type correspond to, say, in the homotopy interpretation, the product space, the coproduct space, the disjoint union, or the function space. These type families, so families of types indexed by other types, they're predicates in logic. So n is prime as a predicate on the natural numbers in logic, or it's a family of sets in set theory, or it's a fibration in homotopy theory. So this A here you can think of as being the base space. Over a point, little x in the base space, I have another type that's the fiber of the base space. So the type family in the homotopy interpretation I think of as being a fibration. And the term family is then a globally defined section of the type family. So that's why some type families had no term families, because these are maps with no section. Some of the fibers were empty in those cases. So these constructions that I sort of skipped over, the dependent product and the dependent sum, construct in the one case the total space of the fibration, so that the space that's on the top, or the space of sections associated to the fibration. They also play a logical role. So if I'm thinking of a type family as being a family of propositions or a predicate on something, these correspond to the mathematical assertions that, again, may or may not be true, that there exists some x and a so that p of x holds, or for all x and a, p of x holds. So if we read the logic column, we've captured all of the sort of primitives in predicate logic with one example, which is equality, and that's the final type family. So I think of a term in an identity type. So this x equals y, a is the type that encodes the mathematical assertion that for terms x and y of type A, x equals y is true. If I have a term in that type that's a proof that x is equal to y in logic, or in the homotopy interpretation, we think of it as a path from x to y. So A you might think of as a moduli space of all whatevers, and points in that space are equivalent in some sense if there's a path between them. So that's the homotopy interpretation. So these identity types are sort of kind of the most interesting, and I mean, this whole table is interesting, particularly if you've never seen it before, but the homotopy types, the identity types especially so. And so I want to briefly mention their rules. So firstly, it's grammatical to ask whether x is equal to y when x and y are terms of type A. So that's sort of the formation rule for this type family. Just forming the type doesn't mean that it's true. So the introduction rule says that for any x, there is a term Riehl, which witnesses that x is equal to x is true. The final rule is somehow very complicated. It captures Leibniz's indiscernibility of identicals, and we call it path induction. So somehow there's a deep analogy between this complicated rule and induction over the natural numbers. And just like you can't show somebody a formal statement of induction over the natural numbers and expect them to know how to prove anything by induction or know how to think about induction, similarly, given the time, I'm not going to be able to make path induction make much sense, but it's as powerful a proof technique for reasoning about equality as induction over the natural numbers is for reasoning about the natural numbers. And in particular, what it implies is that any type in homotopy type theory can be thought of as an infinity groupoid. So if I iterate the identity type family, I can recover an infinity, synthesize an infinity groupoid structure of A that resembles the fundamental infinity groupoid that we talked about at the beginning. So the terms are now the points, the paths are these one morphisms, the paths of paths are two morphisms, and we have all the higher categorical structure, so reversal, concatenation, and it's all proven by this path induction principle. Okay, so the final thing to say about homotopy type theory is that this perspective suggests some new definitions that mirror definitions in topology. So for any type, I can ask whether that type is contractible. So using the propositions as types, this is saying a type is contractible if there exists a term A of type A, so that for all X of type A, there's a path from A to X and implicitly continuously in X. So if I had a term of that type that's giving me a center of contraction and a contracting homotopy, and so that's the sense in which this captures contractibility. And similarly, I can define a notion of equivalence between types, which is a homotopy equivalence. The formula here is a little bit more complicated than you'd expect for a reason that you can ask me about in the reception afterwards. Okay, so now that that's all clear, so it's an infinity category theory for undergraduates. So the central thesis is that if the formal system was more like homotopy type theory, we could teach infinity category theory to undergraduates or to computer. And undergraduates do not need to understand the full details of this formal framework. I certainly didn't know anything about set theory and logic when I was an undergraduate learning how to write mathematical proofs. You learn this sort of informally, and you learn how to write proofs correctly. And maybe later on, you get into logic and foundations and you figure out how this all actually worked. So the formal framework that I'm talking about is something called simplicial homotopy type theory. It was introduced in a joint paper with Mike Schulman. And it's basically homotopy type theory with one new ingredient, which are these axiomatic shapes. They're defined syntactically in a way that I'm not going to explain, but you can think of it as giving a free living directed interval, a free living two simplex, a free living horn, which is a particular part of the boundary of the two simplex. And in particular, then, if I have a type A, I can take functions out of these shapes into that type. And what this means is that in simplicial homotopy type theory, any type has its family of identity types. So that's something that exists in ordinary homotopy type theory. But it has this second family of Hom types whose terms are arrows. So just by virtue of being a type in the system, you have your paths between your points, and you also have your arrows, directed arrows between these points. I can think of the paths as a fiber of some fibration. It's the path space fibration. Similarly, I can think of the arrows as those maps from this shape, the one simplex into A, so that on the source, it's the point X, and on the target, it's the point Y. That's the sort of geometric way to think about these arrows. And what this allows me to do is actually finally define an infinity category for you. So the advantage of this complicated formal system is I can give simple to state definitions. So I'll first say what a pre-infinity category is. And so a type is a pre-infinity category if every composable pair of arrows has a unique composite. So what does that mean? So remember, the idea in infinity category theory is we think of a composition as being witnessed by some two simplex, some invertible two-dimensional arrow, where the boundary paths are, the boundary arrows are the inputs, the F and G, and then the diagonal is the specified composite. So this space of composites, this type of composites, is a subtype of the type of maps from the two simplex into A, so that when I restrict to this kind of spine part of the two simplex, I recover my input arrows F and G. Contractibility is in the sense of homotopy type theory, but when I interpret it semantically in traditional foundations, this corresponds to the contractible moduli space of composites, which I've mentioned several times, but internally to the system, it actually feels like there is a unique composite. And in particular, I get a composition function, which is the thing that I really miss when I'm doing infinity category theory that I'm used to when doing one category theory. It comes back in this formal system. So I am calling this a pre-infinity category, but it's a pretty weird definition. I mean, it feels sort of way too weak in comparison with ordinary categories that have additional structure. So an ordinary category also has identities. Composition with identities is unital. We have associativity. And all of these are actually theorems that follow from the definition of pre-infinity category that I just gave. So somehow asking that any composable pair of arrows has a unique composite implies the existence of identities, implies units, implies associativity. So what is an infinity category? So that has to do with something else. So a pre-infinity category sort of has two accompanying infinity groupoids. There's one that's given by this algebra of paths, and then there's another that's given by isomorphism. So in other words, the arrows that happen to be invertible in the sense of category theory. And so an infinity category is a pre-infinity category where those two groupoids coincide. So if this definition is not familiar, that's okay, because all the theorems I'm about to mention actually hold more generally for pre-infinity categories. I'm going to state them for infinity categories, so they look a little bit more familiar, but they actually just follow from this unique composition condition. Okay, so now I'm going to finally define for you the coproducts and adjunctions. So these, but in the setting of infinity category theory, so two objects in an infinity category, two terms in one of these pre-infinity categories admit a coproduct if there's another object together with a family of equivalences. So for all x and a, I have an equivalence between the type of arrows out of the coproduct into x and the product type of the type of arrows out of a into x and a prime into x. Similarly, I can define adjunctions. So an adjunction is given by a pair of functions. I don't have to say functors because functoriality actually is automatic between pre-infinity categories, infinity categories, together with a family of equivalences. This is the Currian that we discussed previously. So for all A of type A and all B of type B, an equivalence between the type of arrows out of F of A and into B and the type of arrows out of A into U of B. So that's the data of an adjunction. And what I love about this definition is, firstly, it very closely resembles the definitions in one category theory, if you're familiar with them. But in fact, it's actually simpler. So a thing that I emphasized when discussing the innate lemma, were I to give these definitions in one category theory, I would have to say that the families of equivalences are natural in X in the first instance and natural in A and B in the second. That actually follows for free here. So I haven't left anything out. This is the full definition. And in particular, we can reprove that left adjoints preserve colimits. So revisiting the proof that I gave at the very beginning, left adjoints preserve coproducts in exactly the same way. So to show that F of a coproduct is the coproduct of F of the objects, it suffices by the innate lemma to define a family of equivalences involving maps out of these objects into an arbitrary object X. And I get them exactly by composing the equivalences that arise from the adjunction, from the universal property of the coproduct, the adjunction, and the universal property of the coproduct again. So the summary is that sort of distance between one category theory and infinity category theory really collapses by using this different formal system, which has a second advantage involving computer formalization. So the definitions, theorems, and proofs that I just introduced can all be formally verified in a computer proof assistant that knows the rules of this formal system. So I did not explain to you the rules of this formal system, but somebody else, Nikolai Kudasov, explained these rules to a computer proof assistant that's called Resk, after Charles Resk. What I'm going to show you now are screenshots of computer formalizations of some of the things that I've just mentioned. So in particular, we have this definition of a pre-infinity category. A type is a pre-infinity category if every pair of composable arrows has a unique composite. So here is the code that gives that definition, referring to a notion of contractible type that we had to introduce previously into the library. Sort of the style of this, so this appears on a website, which I'll link at the end. The style of the library is we ask the user to write in Markdown some explanation of the code, and then we have an explicit code block that is checked by the computer proof assistant. So in particular, one of the things that I mentioned is that in a pre-infinity category, using the hypothesis that A is in a pre-infinity category, I get a composition function, an explicit function that composes arrows that's defined by just projecting out, extracting the center of contraction from the contractible type. And these are sort of one-line constructions of the composition function and the witness that the composite is a composite. And moreover, I can prove that composition is unique, which is wonderful. This is true in ordinary category theory. It's homotopically unique in infinity category theory in traditional foundations, but in these foundations, it's unique in the sense of uniqueness. And again, so this time the proof is not one line, but it's sort of applying some standard results from homotopy type theory. Okay, so I'll just conclude. So I've also done some formalization or attempting some formalization of infinity category theory and other proof assistants, specifically Lean. This is considerably easier because we brought the formal system a lot closer to the mathematical object of study. And in particular, this really feels like something you could teach to undergraduates because the collapse between infinity categories and one categories has disappeared. Of course, there's a cost to learning a new formal system, but a computer proof assistant can really help there. In particular, if you're making a mistake, the computer might tell you that you're wrong. And in fact, we were wrong in the published paper that I cited in sort of a silly way. There was an error of circular reasoning that I caught when I formalized the same result in RZK several years later. So this is not yet a complete formalism for infinity category theory. There's theoretical limitations to the system, but there's folks who have been working on that. I'll stop there. Thank you.
Thank you for an amazing lecture. And before we come to the smart questions in the room, I just wanted to ask you, so you described your dream of teaching this to undergraduates. What is the obstacle to turn your dream into reality? Is it just the difficulty of the concepts, or is it your administrators don't want you to?
Right. Sure. So I guess there's sort of several things. I mean, so the meta framing for this is, I fear that mathematics is getting more and more complicated, and papers are getting longer and longer, and people are understanding them less and less well. So I'm really interested in things that push against that trend. And the idea that I've presented here is in infinity category theory, but potentially also in other areas, to look for some sort of synthetic foundation system that brings the foundations closer to the sort of mathematical objects you want to study. So what I like about this is this, I did not leave any details out of the proofs that I gave. There, everything is there. You can, see it in the formalism. You can verify it in the proof assistant. So I'm not shortening my papers by skipping a lot of steps that it would take a lot of expertise to fill in. I'm shortening my papers by sort of relying on a very expertly designed system, formal system that makes everything precise. So what are some challenges? I mean, firstly, it's difficult to learn how to write proofs in a new formal system. I went through this experience when I was a sort of junior professor. I learned traditional foundations implicitly, and then at some point I started writing proofs in homotopy type theory, and I had no idea if my proofs were correct. I felt like I was back in high school, and is this a proof of this theorem? I have absolutely no idea. What helped me get around it was the experience of using a computer proof assistant. So I taught homotopy type theory, which is sort of how you learn anything when you're a faculty member, and wrote all the homework for that paper in the computer proof assistant AGDA. And in that process, there were a lot of small mistakes that I was skipping. There were things I didn't yet understand about this new formal system that I caught immediately by trying to do it in a computer proof assistant, which would sort of, I would state something and it would tell me it was wrong. I would write a proof, it would tell me it was wrong. And then very quickly my intuition improved. So I really only think this is realistic to expect an undergraduate to prove theorems about infinity category theory in a new formal system if they're using a computer proof assistant. So RZK exists, RESC exists, so that is a possibility. It's not maybe the most user-friendly experience. The hardest part of this talk was the homotopy type theory section. I mean, that is kind of a big ask. I think an undergraduate who knew homotopy type theory could absolutely do infinity category theory, but there's not that many undergraduates who know homotopy type theory. Another issue, though, is the one that I mentioned here, which is that the simplicial hot, which is the formal system that made everything that I just presented rigorous, is not powerful enough to even correctly state all theorems about infinity categories, much less use them. So if you're trying to learn infinity category theory because you want to read Farag-Schulze, this won't teach you enough infinity category theory yet. So there's folks that are working on that. The final system is going to be more complicated and needs modal extensions of simplicial hot. There's not a proof assistant for those modal extensions yet. So I would say that the theory is still under development, but maybe in 10 years, certainly in 100 years, which is what I've said in the past. So.
Great.
But I appreciate that vote of support. So.
It makes me think of, the programming language Lisp. I don't know if you're familiar, but this idea of you rebuild the language to better fit your situation. But then it makes me think like, well, should you just have a different foundation for every branch of mathematics, or I don't really know in what context it makes sense to care that much about foundations we necessarily apply everywhere. Or
Yeah, so I'll paraphrase the question by saying, should there be a different foundation for all kinds of mathematics? So I'm of the minority point of view that this is something we should be exploring. And I mean, of course, mathematicians in different areas talk to each other, so we care about interpretations of one foundation system for another. So right now, people are trying to build a bridge from homotopy type theory, the foundation I mentioned, into the computer proof assistant Lean. You can't directly write a proof in homotopy type theory in Lean because Lean treats equality in a very different way, but there's a sort of complicated way to interpret homotopy type theory in Lean, and people are in the process of formalizing that right now. If we had all of these systems that would allow simple proofs as long as you stay in one subject area, together with very difficult to define interpretations, then we could sort of have both worlds, a synthetic framework for doing one sort of mathematics as well as this mode of communication. I realize this is going to be quite complicated, but again, I want something that's going to let me write shorter proofs in my area while still being rigorous.
Before your talk, I was surprised that you use RZK as a full proof assistant, because of course the natural home maybe for that type of theory would have been Coq, the coordinate sort of assistant, which is really based on almost types. I think they held a workshop in Princeton that a year ago. So why that didn't quite fit infinity categories with Coq?
So thanks for that question. So the question is why I'm using the proof assistant RZK rather than what's now called ROC or AGDA or something like that. And so right, there are other possibilities. There are other proof assistants that could be used to formalize this stuff. Lean is not one of them because we need a different meaning of equality, but in ROC or in AGDA, this is possible. The reason I'm using RZK is that there's a second ingredient to the simplicial homotopy type theory as specified in that paper that I didn't mention today, which is something called extension types. Essentially what it means is that these fibers that were used to define the type of arrows are kind of strict fibers rather than homotopy fibers. If I were doing this in ROC, I would be working with the homotopy fiber here rather than the strict fiber. And then the data of an arrow would involve firstly a map from the one simplex into A, which is the data that I want, but also some paths connecting f of 0 to the point X and connecting f of 1 to the point Y. And that's a bit of extra crud that I'd rather not have. So RZK implements extension types that allow me to use strict fibers rather than homotopy type fibers. I'd have to use a weaker version, an equivalent type, but something a little bit more annoying to work with in ROC or in AGDA. I'm not trying to use ROC right now just because I have less familiarity with that system, but we are reformalizing some of this in AGDA right now, just to sort of see how painful it is to do without the extension types.
I realize we're a little over time, but we can take another 1 or 2 questions if there's interest. I think you were first.
Sure. So at the moment, the way undergraduate education works a lot of the time is, at the start of university, students take sort of a naive set theory course, and then they sort of do the rest of their undergraduate maths, and then maybe if they have interest, they do a course in mathematics set theory, and then after. So, if in 50 years, like the foundation of maths changes to type theory or many type theories, does undergraduate education change at all?
I am of the point of view. So the question is, does undergraduate education change in the future vis-a-vis its treatment of foundations? I'm kind of the point of view that if we're doing an implicit foundation rather than an explicit foundation, we might as well do something like dependent type theory as opposed to set theory, not necessarily dependent type theory in the sense of homotopy type theory as I was emphasizing today, but dependent type theory in the sense of the extensional dependent type theory that's used in the computer proof assistant Lean. For me, I found it easier now that I know some dependent type theory to correctly or clearly, unambiguously state mathematical theorems. It's also, of course, easier to use a computer proof assistant if you speak the language of the computer proof assistant. So I am interested to see how this evolves. Of course, set theory is still an interesting area of mathematics and will continue to exist. But if we're being implicit or sort of informal in the way we're teaching foundations to undergraduates, I think we could swap them out without it making such a big deal.
Hi, so it's the question is in two parts. The first part is a bit wacky. Basically, this comment about the infinity groupoid being an animus of the or anima of the set, is that a kind of Jungian illusion, which is a cryptic hint that there is actually a shadow as well, which is a non-trivial space of some interest? Is that what they're trying to say? And the second part, would you teach this before group theory or after group theory?
Great. Okay, so right. So the question about where did the term anima come in, I have to defer to Schultz. I have absolutely no idea. So no comment on that. Would I teach this before or after group theory? 100% after group theory, because I would not teach category theory before group theory. I'm personally a little bit conservative about the ideal point in an undergraduate's education to learn category theory. I like it as sort of a final year undergraduate or a master's course, an ability to revisit the mathematics that you've discussed, and in the context of all those mathematics, really have this abstraction enlivened by examples. So that's my personal point of view. So if this is something at the undergraduate level, it's at the very tippy top of the undergraduate level, definitely not before group theory. No.
Great. I think we have to leave it there, but there's more opportunity to discuss with Emily in the reception and over dinner. Dinner will be at 7:15 if you have registered. And just remains to thank Emily again and also Clark for really brilliant, inspiring lectures. So thank you very much.